Parametric retrofitting of bench equipment for remote lab access. Project summary. Our project aims to retrofit with full remote access capabilities for the gantry crane pendulum in a removable, non-destructive manner. We separate the physical from the software and connect it through a Raspberry Pi as the interface in between the student's commands and the hardware. The goal is made so it can give the closest experience to normal hands-on experimentation with the equipment, from real-time controls, video feedback, and other functions to maintain it safe and reliable. Proposed solution replaces physical ISA connection from the PC to the physical experiment with a TCP connection between student laptop and remote lab. Adds remote monitoring and physical control of remote lab from the student laptop, and provides connectivity, scheduling, and monitoring by the lab manager. Subsystems include the physical experiment, button actuators and cart centering, experiment interface, visual monitoring, and student access. The physical experiment. The gantry pendulum from Feedback Systems is the experimental device that we chose to automate. In order for us to be able to automate the device, we had to learn how to use it, which is different from normal devices. In order to make it work, we had to procure an old computer with a PCI slot for an old version of a PCI DAC card that can interface with the device. Once we got the parts, we put it together and tried to make the device work as designed. However, it had some odd behavior, and we realized that it was damaged and not working correctly. We took apart the device and started tinkering with it and realized that the encoders and decoders are not exactly working the way they're supposed to report the cart position and the angles of the pendulum. We fixed the angle problem with the pendulum by replacing the encoder. However, replacing the encoder for the cart position didn't fix the problem, which means it's got to be the decoder chip. The decoder chips have been purchased, and we're waiting for shipment so that we can install them, and hopefully that will resolve all the final problems with the physical experiment. Once the physical experiment is ready to run as intended by the manufacturer, we can then begin to decode all the signals that are coming from the device so that we can replicate it with our Raspberry Pi interface. Button actuators and cart centering.
The start and stop functions are implemented with push-button switches. The controller for the device already has physical start and stop buttons. For remote control, small servos will rotate and press the physical buttons. The gantry will have a limit switch added to detect whether the cart is centered, for a total of 3 limit switches. The center limit switch will be used for the centering function. Start, stop, and center buttons are necessary for the operation of the device. The start button is used to run the Simulink code for a given experiment. The stop button is used to interrupt an experiment and is a necessary safety feature. The center button is necessary for remote operation so that each experiment can be run with the same starting conditions without physical access to the device. This subsystem will interface with the experimental interface subsystem for remote control. Its microcontroller will activate the corresponding servo motor for each of the remote controls. These additions are non-destructive to the original device. Known challenges include ensuring that the centering function doesn't bring the cart too far to either side of the gantry and pushing the start and stop buttons with the servos. Unknown challenges include finding out whether the cart centering function can work by using the existing motor on the cart. The early prototype will have physical servos and limit switches. Remote functions will include start, stop, and center commands on the Raspberry Pi interface.
Experiment interface replaces the existing ISA connection between Simulink and the physical experiment with a logical connection over TCP/IP. Interface is a Raspberry Pi, which takes the actuator signals from the remote laptop and passes the signals via the I2C protocol to the actuator signals module. The DAC in this module provides the control voltage to operate the experiment. Return data is captured by the GPIO expansion and read by the Pi via the I2C interface. The Pi returns the data to the data collection module. I2C is a universal interface giving the flexibility of changing the equipment interface to either a microcontroller or desktop system if necessary. Interface connects all subsystems together. It connects Simulink to the physical experiment, provides a video image to the laptop, generates a signal to push the physical buttons, and enables student to access to the physical lab. There are two challenges for this solution. Can the real-time control and data collection be preserved between the physical experiment and Simulink? Secondly, can the connection between the laptop and the physical experiment remain secure? These challenges will be answered during the implementation phase. So what have we implemented? Well, we have access to the GPIO I2C signals from the Raspberry Pi, and we've also breadboarded the actuator signal and return data modules, which will connect the Raspberry Pi to the physical experiment.
Let's talk about the visual monitoring aspect of our project. Components include a USB camera, probably a Logitech C920, though not fully sure. I believe cheap, reliable, decent quality camera should do the trick. That was just the main one, the first one that showed. Raspberry Pi or the PCSI streaming processor. Most likely is going to be the Raspberry Pi where we have that most of that set up. And well, for justification, well, 1080p, I think it's a good resolution, and something that can maintain that resolution should be the best to be able to maintain the experiment also observable and to achieve the closest to the real experience as remote shooting could get. And the processor, well, it's needed to handle the video encoding with low latency. Then the monitoring will interface with the website, the Django, by being embedded into it for the real-time viewing. Then also we'll have to work on the access control functions website, so only authorized users can view the live feed during their authorized session, not anytime also. Just that arrays come from low latency streaming that needs to maintain synchronous with the experiment behavior, ensuring reliable operation over long periods. So we also have to think about what to do if the camera resets, if connection starts becoming a little spotty. We need to make some plans for that. Ensuring that the streaming stays secure in different networks, not just the local one. And then for possible prototypes, we can just do a basic camera mounted near the experiment, then stream it through a simple web page, and that's it. Now really, there's no authentication wouldn't be needed at this point, or any other interface into the other systems. It's just mainly to show that it will work.
My name is Evan King, and I will be working on the remote student access portion of the system. So the two main components of the student access portion of the system are going to be the Django web interface and the MySQL database. I chose Django for the web interface because it has many built-in functionalities that work well for what I want to do with the site, such as MQTT and storing login information. It organizes the different views and their corresponding functions as well, with different Python files to achieve different functions and the different HTML views to have the different pages in the site. It also will make it easy to add the live video feed later down the road. I chose MySQL for the database because it's user-friendly and it stores all the information that I need, such as the readings received, the commands sent, and the user information. For the system to work as intended, the Django site will have to interface with all of the other subsystems. This includes the Raspberry Pi, which the Django site will send commands to and receive readings from, and display them to the user. For the live feed, the Django site will allow for a link to a live feed to be presented on the screen to the user. This is so that the user can see how the system is being affected by the commands they sent. For the button actuators, the Django site will have a custom command box that the user can type custom commands into or send quick commands with the buttons. This will be processed by the Raspberry Pi and sent to the button actuators that will help control the system. Some of the challenges I have yet to face include configuring the live video feed so that there's low latency and delay while it is being shown to the site. This is so that the user can see exactly what is happening with the system as they are sending these precise commands. Another challenge will be having these precise commands read exactly how they are typed and translating that to exact system movements, exactly how the user wants. Another potential challenge would be instructor verification for login, verifying that someone is an instructor before they're allowed to have the instructor role on the site, as it grants additional permissions. For the early prototype that I've developed, some of the features include login verification, where the user creates an account with either a student or instructor role and is shown the corresponding view. User data storage, all of the user logins, commands, and readings are stored in the MySQL database. Right now, messages can be sent to and received from MATLAB. They're sent to MATLAB with the quick command buttons and the custom command text box, and they are received from MATLAB, and all of these are displayed on the web page. All data sent to and from the site are also attributed to their user and only presented to them on the data history page. This is so that the user only sees the commands that they have sent and only gets the readings that they have received from the system during their experiment.
The project schedule. Our project schedule and timeline is variable because we are still trying to sew up some of the smaller details. However, I believe that our goal is to be done within 20 weeks. I have, for our first milestone, which is going to be 3 to 4 weeks, will be to get the apparatus, the device to be fully functional and be able to work as designed. We are going to prepare an interface microcontroller, which we've already begun to do with the Raspberry Pi. And we're going to build the website interface to display the experimental data and the apparatus controls. A lot of this is already in works and hopefully will be done soon. In milestone 2, we will demonstrate the apparatus as designed, send and receive signals from the apparatus using the microcontroller interface, build a database to store information from the experiment for reporting purposes, design a communication protocol for sending and receiving information from the website to the microprocessor and from the microprocessor to the device itself. Milestone 3, which will be 4 to 6 weeks, we will install Simulink on the microcontroller to handle some of the experiment's communication, design experiments similar to the ones in Simulink with the new communication protocol, build a user login interface to allow different users to make profiles. However, only one user at a time will be able to control the device, although many users can watch the experiment at the same time. Display video of the device as it is working. Button actuators to work the start and stop the device, and a cart positioning system to center the cart in the apparatus. Finally, for the final project schedule timeline, milestone 4, which will be 4 to 6 weeks, will round out our device and our presentation. Users will be able to log into the web interface with their profile and observe the current state of the experiment. Video will be streaming. Reporting on previous experiments will be available. The user can operate the experiment if it's idle. Button actuators are working, the cart centering is working, and the experiment execution is working as designed by the manufacturer. Our microcontroller communicates with the apparatus to control the experiment, and the microcontroller communicates with the web interface for commands and to report data. In very broad strokes, the tasks have been assigned by category. I, Skylar Gutman, will be working on the experiment equipment. Bruce Fong will be working on the experimental interface with the Raspberry Pi. Evan King is working on the web portal and communications using the Django, Python, and communication protocols. Device enhancements and manipulations will be done by Boone Douglas, who will work on button actuators, cart centering, and any other modifications that need to be done. And video streaming and Simulink streaming will be handled by Angel Diaz. Of course, we'll all be interfacing with each other, so we'll be working and helping each other on different effects of the project.